Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Count number of maximum bitwise OR subsets, Leetcode 2044. In this problem, we are given an array of nums and we have to find the maximum possible bitwise OR of a subset of nums. And we have to return the number of different non-empty subsets with maximum bitwise OR. In subsets, elements don't have to be contiguous or in any order. For each number, we can either choose to include it or ignore it. Two subsets are considered different if the indices of the elements chosen are different. The bitwise OR of an array A is equal to bitwise OR of all the elements in it. Then in example 1, for the given array nums, the maximum possible bitwise OR of a subset is 3, which we can either achieve just by number 3 or we can do the bitwise OR between 3 and 1. Binary representation of 3 is 1, 1 and binary representation of 1 is 1. So in bitwise OR, when any of the bit is set, the output also has a bit set. So because here we have two subsets with bitwise OR of 3, we will return output as 2. Similarly, in example 2, we are given array of integers containing only 2's. So bitwise OR of any of them will be equal to 2. So in this case, it behaves like a normal subset problem where total number of subsets is 2 to the power of 3, but we have to remove the empty subset. So that's why total number of subsets will be 7. And finally, in example 3, the maximum possible bitwise OR is 7 and there are 6 subsets with a bitwise OR of 7. So we will return 6 as our answer. Now in terms of solution, first thing we notice that bitwise OR operation is a cumulative operation. That is, once the bit is set, it remains set. So this means the result of ORing two numbers is never smaller than either of the individual numbers. So 0 or 3 will give us 3, that is a number itself. Similarly, if we do the bitwise OR of a number with another number, it can either stay the same or we will get a bigger number. For example, when we did 3 or 1, we got 3, which is equal to 3 in this case, or more than 1. So in any case, either we can get the same number or we can get the bigger number. So that means including more and more elements in the subset typically brings the result closer to the maximum possible value. So we can get the maximum OR by taking the bitwise OR of the whole array. For example, for nums equal to 3 to 1, 5, we will do 3 or 2 or 1 or 5, which will be equal to 1, 1, 1 in binary. So 7 in decimal form. So that will give us max OR value of 7. Now our next step is to count how many subsets achieve this maximum. So this now becomes like a subset problem where we have to generate all the subsets of an array, but here we want to count them. However, the logic stays the same. If you like to know more about it, please check out the I button. So now for calculating the subsets, for each element, we can either choose to include it or exclude it. For example, for 3, we can either include it or exclude it. Or again, for 1, we can either include it or we exclude it. And this will result in an empty set, but we don't want to include the empty sets here. And in this problem, anyways, we cannot have empty set because if we OR a non-zero number with another number, we will always get some non-zero OR value. And in this problem, in the constraints, it is mentioned that elements in the array have a range 1 to 10 to the power of 5. So that means elements cannot be 0. So empty sets are anyways ruled out. This inclusion or exclusion can be done with the index on the array. At any point, we can either choose the element on the index or we can exclude it. And we will also define the variable current OR to track the OR value of current subset. So each time we choose to include that number, we will perform the OR operation with that number. And on exclusion, we skip the operation. And what will be our base condition? Our base condition will be once we reach the end of the array, that means we don't have any more elements to OR with. And in this case, we will check if our OR value is equal to maximum OR. Then we increment our result or counter by 1. And finally, we return count as our answer. So now let's see the code part. So first we will define the max OR variable to store the maximum value of the bitwise OR operation in the current array. And then we will calculate it by looping on the nums array and perform bitwise OR operation with the current number. And now we can start the DFS logic. In our case, DFS will return number of subsets that achieve maximum OR value starting with index 0 and initial value of OR operations will be equal to 0. Let's also define some class level variables so that we don't have to pass it to the DFS function. And as a programmer, we can focus on the arguments that really change in the DFS function. So one variable can be nums array and another one can be max OR value because they won't change during the iteration. and we can initiate them inside count max or subsets function. Now let's write the DFS logic to explore all the subsets. So we will pass in the index of the current element that we are considering for the subset and current value of OR operations for the given subset. Our base condition will be if we have considered all the elements, that is, we have reached the end of the array. So if that is the case, we will return our answer as 1 if current OR value is equal to max OR. Otherwise, we will return 0. And now for the number at current index, we can either include that number or we can exclude it. So first let's write the include case. In the include case, we will call the DFS, passing the index for next element because we can take this number only once, and update the XOR value with current number's value. But if we exclude it, it will be very similar to previous case, but we will not include this number in the OR operation calculation. And finally, sum of results from both the cases will be our answer. So now let's run this code. Cool, let's submit this code. Cool, in terms of time complexity, it will be O of n into 2 to the power of n, where n is number of elements in the array. Because at each call in the DFS, we either include the element or exclude it. Because of this, the time complexity is 2 to the power of n. And then we are going through n elements in the array to calculate the current OR value. So because of this, the time complexity is O of n into 2 to the power of n. And in terms of space complexity, it will be O of n because we are using the recursion stack in the DFS. And the recursion can go n levels deep because it depends on index value. And index value belongs to range 0, n minus 1. So because of this, the space complexity is O of n. And two more points on the DFS. Instead of calculating the max OR value by running the loop, we could have also calculated the max OR value in the DFS by doing the comparison on the current OR value during different DFS calls and tracking the maximum among them. But that would complicate the DFS logic and also violate the single responsibility principle because now DFS has to calculate the maximum as well as count the max OR subsets. So luckily this loop did a trick. And another point is we can also use memoization. But because this is a backtracking solution, it may not be very helpful. If you are interested in that approach, please check out the code link in the description below, where I have covered both the approaches. So that's it. I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. If you have any questions or suggestions, please write them in the comment box. Thanks for watching. See you next time.